For a long moment, the universe seemed to hold its breath. In the black stillness beyond the orbit of Mars, an object that had been moving through space for millions of years, streaking between the stars, burning with ancient sunlight, suddenly appeared to stop. Its trail froze, its motion vanished. Telescopes tracking it from observatories across Earth kept their lenses trained on that faint speck of light. They waited for the familiar drift, the incremental shift against the star field that always came with time. But the shift never arrived. The coordinates didn't change. For the first time in recorded history, astronomers were watching something that refused to move. The object was known as 3I/ATLAS, the third confirmed interstellar visitor ever to enter our solar system. The I stands for interstellar, and the 3 marks it as only the third of its kind, following the famous Oumuamua and Borisov. But this one would become far stranger than either. 3I/ATLAS had been gliding inward on a hyperbolic path, a clean, predictable arc that meant it wasn't bound by the sun's gravity. It came from deep interstellar space, destined to swing around the sun once and vanish back into the darkness. Everything about it, its composition, its trajectory, its chemistry, fit the textbook model of a comet, until it didn't. The first reports came from the Pan-STARRS Observatory in Hawaii. Their team noticed that successive exposures showed no motion relative to the background stars. The same signal appeared again from Chile, then from Spain, then from South Africa. Within a day, the message spread through astronomy networks. 3I/ATLAS appears stationary. At first, nobody believed it. Data gets messy all the time. Bad weather, sensor lag, calibration errors. But the stillness persisted. It wasn't a single instrument or a corrupted image. The same reading came from different continents, different telescopes, and different nights. When scientists tried to predict its next position, they found nothing matched. It wasn't moving along its expected path. It wasn't drifting sideways. It wasn't dimming or flaring. It simply hung there, motionless, silent. Impossible. For days, astronomers stared at their screens in disbelief. The idea of a celestial object standing still violated every known law of motion. Yet 3I/ATLAS defied them all, like a frozen clock in the middle of eternity. The story of 3I/ATLAS began like many other cosmic discoveries, quietly with a faint smudge of light. It was first noticed by automated sky surveys, part of an endless network of instruments scanning the heavens for moving points. To the computers cataloging them, it looked like just another comet. But when analysts examined its orbital parameters, they realized it wasn't part of our solar family at all. Its path was hyperbolic, so open that nothing could reel it back in. This object was a visitor from another star. At first, the find drew little attention. Astronomers had already seen interstellar wanderers before. Oumuamua, discovered in 2017, and Borisov in 2019 had already shown that the galaxy occasionally sends messengers our way. Most assumed 3I/ATLAS would behave the same, a cold fragment of ice and dust, flaring slightly as it approached the sun and then fading back into the void. For weeks, that assumption held true. Its trajectory was plotted, its composition analyzed, its brightness monitored. The data suggested a fairly normal comet, shedding faint gases as it warmed. NASA logged it as a transient object of interest, notable but unthreatening. Then came the night that changed everything. When teams compared exposures taken over consecutive nights, something immediately looked off. Normally, even at vast distances, a comet's position shifts slightly against the background stars. But 3I/ATLAS hadn't budged. Its coordinates were identical down to the fraction of a pixel. The observers thought it was a mistake. They recalibrated their telescopes, checked their clocks, and reprocessed the data. Still, the same eerie stillness. To rule out error, they cross-referenced images from other facilities. Each confirmed it. No change, no drift, no motion. The emails began flooding in between observatories. Check your tracking systems. Verify alignment. Confirm exposure times. Every check came back clean. Across the world, astrophysicists stared at the numbers, unable to reconcile them with the laws of orbital motion. An interstellar object traveling tens of kilometers per second does not simply stop. It cannot pause mid-flight like a bird caught in invisible glass. Yet, that is exactly what the data showed. The silence that followed in research channels felt heavier than discovery itself. Something had happened out there, something that broke the most fundamental rule in the universe, that everything moves. In space, there is no such thing as stillness. Every planet spins. Every asteroid tumbles. Every grain of dust drifts along invisible gravitational lines. Even the faintest particle, caught between stars, moves in response to forces so ancient and unyielding they define the shape of the cosmos itself. Motion is not an option, it is existence. So when astronomers saw an object stop, the idea felt like a fracture in reality. The laws that describe motion are among the oldest and most certain in science. Newton defined them centuries ago, Einstein refined them, and every spacecraft ever launched has relied on them. Gravity pulls, mass accelerates, trajectories can bend, but they never break. For a comet on a hyperbolic path, speed is constant and predictable, faster as it falls toward the sun, slower as it escapes. But under no circumstances does it pause. Yet 3I/ATLAS had done just that. NASA's Jet Propulsion Laboratory received the initial reports with disbelief. They ran orbital simulations to check for anomalies in gravitational influence. Perhaps a planet or large asteroid had altered its path. Nothing fit. The comet was too far out, too isolated, and moving too fast for any gravitational interaction to hold it still. If not gravity, then maybe light. Sometimes optical illusions can trick observers. A change in brightness, an alignment with background stars, or a sudden dimming that hides motion in plain sight. But this wasn't a trick of the eye. The data came from multiple wavelengths, optical, infrared, and radio, and every channel told the same story. The stillness wasn't an illusion. In chat logs between observatories, researchers began using the same phrase. It's locked. Locked, as in suspended. Locked, as in trapped between two invisible hands that neither pushed nor pulled. The more they analyzed the images, the clearer it became that the object's velocity vector had gone flat. The numbers on their screens refused to change, and for those who dedicate their lives to measuring motion, that was the most unsettling sight imaginable. Somewhere out there, in a space that has never stopped moving, a comet older than the sun had decided to stand still, and no one on Earth could explain how. When the impossible happens, science begins with the simplest explanation. If 3I/ATLAS had somehow stopped moving, perhaps it hadn't been stopped at all. Perhaps it had been pushed. Comets are notoriously unstable bodies. They're not solid rocks, but porous conglomerates of dust, ice, and frozen gases. As sunlight heats them, those gases erupt through cracks and vents, forming powerful jets that act like tiny thrusters. For most comets, these jets create small deviations, nudging them slightly off course, changing rotation rates, or making them flare unpredictably. So the first hypothesis was straightforward. Maybe 3I/ATLAS had released an enormous jet in the opposite direction of its motion, just strong enough to counter its forward speed. In effect, it would be braking, temporarily canceling out the velocity that carried it through space. It sounded plausible, at least until someone did the math. The object was traveling at tens of kilometers per second, fast enough to cross the distance from Earth to the Moon in a few hours. To counter that motion, a jet of gas would need to exert a thrust comparable to a major rocket engine sustained for hours or days, and it would have to do so with perfect balance, matching the comet's direction and speed exactly, or the object would veer off or spin violently. That kind of stability is unheard of in nature. Outgassing is chaotic, erupting from irregular surfaces without symmetry or control. No known comet has ever generated that kind of precise counterthrust. Then there was the evidence itself. Spectral readings showed no surge in emissions, no heat spike, no violent venting. The coma surrounding the nucleus remained calm. Even the light curve stayed steady. No brightening, no flicker. If a massive jet had fired, it would have left fingerprints all over the data. There were none. The more they searched for proof, the less sense the idea made. Nature doesn't pause so neatly. So, the jet hypothesis, the only remotely conventional explanation, collapsed. And with it, the fragile comfort of believing that this event could still fit inside known physics began to crumble too. If not an eruption, then what had held a comet still against the endless pull of the stars? When conventional science reaches its limits, imagination steps in, not as fantasy, but as necessity. The moment 3I/ATLAS broke the rules of motion, every safe, standard explanation fell away. And what replaced them were theories that sounded more like cosmic speculation than astronomy. Yet for a brief time, these were the only ideas left on the table. Inside NASA's Goddard Space Flight Center, researchers began sharing messages that read less like data reports and more like thought experiments. Could the comet have encountered an unseen force, a magnetic current, a plasma eddy, or a patch of distorted space-time? Could something in the sun's extended magnetic field have reached out and momentarily pinned it in place? No one wanted to say those words out loud. They carried a weight that implied the universe itself might not behave uniformly. But as the evidence piled up, silence felt like denial. Plasma physicists were among the first to speak. The space between the planets isn't truly empty. It's filled with solar wind, charged particles flowing outward from the sun at incredible speeds. That wind carries embedded magnetic fields that stretch for millions of kilometers, twisting and folding as they interact with planets and interstellar currents. Under rare conditions, those fields can create turbulent regions, pockets of electromagnetic chaos where the forces nearly cancel each other out. If 3I/ATLAS had wandered into one of those regions, it could, in theory, experience a kind of magnetic drag, a momentary suspension between opposing streams of charged particles. Like a leaf caught between two colliding gusts of wind, the comet might have appeared still because every force acting upon it had reached equilibrium. The idea had elegance, but also problems. Magnetic fields at that distance from the sun are incredibly weak, far too faint to stop an object the size of a mountain. For a body moving at tens of kilometers per second, the energy needed to halt its motion, even briefly, would be astronomical. There wasn't enough power in the solar wind to do it. Others turned to light itself. What if the comet hadn't stopped at all? What if its image had? Gravitational lensing, the bending of light by massive objects, is a known and measurable phenomenon. Under the right alignment, a body passing through a distorted field of space-time could appear to freeze as light from it takes different paths to reach us. Maybe, some suggested, 3I/ATLAS had crossed a subtle gravitational boundary, where light bending caused a temporary illusion of stillness. It was an elegant solution, one that fit comfortably within Einstein's equations, but it required a precision of alignment so extreme that it bordered on impossible. The sun, the Earth, and the comet would all need to occupy a configuration nearly perfect to the degree. And yet, the possibility lingered, because improbable isn't the same as impossible. As those models were debated, a quieter, stranger idea began to surface, one that crossed into the territory of the unknown. Some theorists proposed that the comet wasn't entirely passive. Maybe it wasn't just a frozen relic being pushed and pulled by external forces. Maybe something inside it had changed. Comets are layered time capsules, filled with ices and materials older than the planets themselves. As they heat, volatile compounds within can shift from solid to gas, building pressure deep below the surface. A sudden phase change, a release of trapped energy, could theoretically alter internal balance. But 3I/ATLAS had behaved too precisely for random venting. Its halt was too smooth, too clean. The whispers grew bolder. Could 3I/ATLAS be responding to something? Could it be interacting with the fields around it, not as an object being acted upon, but as something capable of reacting almost intelligently? NASA didn't endorse the speculation, but it didn't dismiss it either. In one internal report, a line stood out. If external causes are ruled out, internal mechanisms must be considered, however unconventional they may seem. That sentence circulated through research networks like a quiet revelation. For the first time, official science acknowledged the unthinkable, that the object might be doing something to itself. The event began to draw comparisons to Oumuamua, the first interstellar visitor, which had also behaved oddly, accelerating slightly as it left the sun, without any detectable jets or thrust. That anomaly had been explained away but uneasily. Now with 3I/ATLAS appearing to stop altogether, the questions returned stronger than ever. Was this how interstellar bodies behaved when they interacted with environments far different from where they were born? Were these strange dynamics the natural physics of alien material under alien stresses? Or was something else guiding the motion, something built into the comet's very structure, something the laws of our solar system were never meant to describe? Whatever the answer, one thing had become clear. This was no longer just a story about a comet. It was a story about how far human understanding could stretch before it began to tear. In the search for answers, one theory began to rise above the noise. It came not from astronomers, but from plasma physicists, scientists who study the invisible ocean of charged particles that fills our solar system. They proposed that 3I/ATLAS had stumbled into a magnetic snare. The sun's magnetic field doesn't end with its surface. It stretches outward for billions of kilometers, woven into the solar wind like filaments of energy. As that field interacts with interstellar space, it twists, folds, and forms structures we barely understand. Somewhere along that vast interface, currents can collide, creating eddies, zones where magnetic and electric pressures nearly cancel out. In such a region, a metallic body could, in theory, experience temporary suspension. It would neither accelerate nor decelerate, locked momentarily in magnetic balance. The data gave this theory unexpected weight. Spectral analysis from infrared and radio telescopes revealed something unusual in 3I/ATLAS's composition. Traces of nickel, cobalt, and magnetic silicates, materials that could respond to electromagnetic forces. If those magnetic minerals were aligned just right within its nucleus, the comet might have acted like a natural conductor, coupling briefly with the sun's magnetic field. The result would be apparent stasis, a kind of cosmic resonance where the object was neither free nor trapped but hovering in energetic equilibrium. It was a stunning idea. A comet, billions of years old, accidentally caught in a magnetic lock between stars. But as the data accumulated, another puzzle emerged. During the still phase, 3I/ATLAS's thermal signature began to oscillate. Temperatures on its surface rose and fell in regular pulses, as though something inside it were responding to the environment in cycles. And that led to an even stranger question. Was the comet stabilizing itself? For those who refused to accept any form of self-regulation, another possibility remained. What if the comet hadn't actually stopped? What if space-time itself had bent in such a way that it only looked motionless to us? Physicists began exploring gravitational lensing and relativistic optics, phenomena that occur when light curves around massive bodies. If 3I/ATLAS passed through a region where light was distorted, the image of the comet might freeze even while it continued to move. In that case, what appeared as stillness was actually motion hidden behind a cosmic mirage. It was a comforting explanation, an elegant one, but it came with its own impossibilities. For a lensing effect to last long enough to simulate a complete stop, every alignment would need to be perfect. The Sun, Earth, and the comet would have to occupy a geometric relationship so precise it would border on miraculous. Then came the spectral data. During the stillness, 3I/ATLAS's emissions flickered between red and blue shifts, as though oscillating between moving away and moving toward Earth at the same time. No known natural process could produce that pattern. The effect looked almost like quantum interference, a macro-scale version of particles behaving as waves, existing in overlapping states of motion. To many, that seemed absurd, but to a few, it opened a door. If a comet made of exotic interstellar material passed through regions where magnetic and gravitational forces overlapped, perhaps it could resonate at frequencies that caused light and time to behave differently around it. And that would mean 3I/ATLAS wasn't merely a rock in space. It was a bridge, matter large enough to make the microscopic rules of quantum physics visible to human eyes. In the aftermath, NASA assembled a special working group, astrophysicists, material scientists, plasma theorists, and mathematicians, tasked with building a single, unified model to explain what had happened. Thousands of simulations were run. Most failed. Only a few succeeded, and only under conditions of perfect balance between solar radiation pressure, magnetic flux, and gravitational drag. That balance produced a state where motion nearly vanished, a phenomenon later called dynamic null equilibrium. 3I/ATLAS, it seemed, had wandered into one of those null zones, a place in space where forces meet and cancel so precisely that relative motion disappears. That discovery changed how we view interstellar travel. It suggested the galaxy may contain invisible boundaries, regions of gravitational neutrality where objects can drift without acceleration. If humanity ever builds ships to cross the stars, these zones could become cosmic rest stops, natural harbors scattered across the void. A comet had found one by accident. Then, one night, it moved again. The data came in quietly, almost anticlimactic. The numbers shifted, fractionally at first, then steadily. The comet had resumed its journey. Its velocity was slightly altered, its brightness changed, its spectrum subtly redder, as if something inside it had been transformed. Across observatories, relief washed through control rooms. The laws of motion had reasserted themselves. The universe had started ticking again, but no one who had witnessed those frozen nights felt the same. They had watched an interstellar traveler defy motion itself. They had seen physics hesitate. In the months that followed, the story of 3I/ATLAS reshaped astronomy. Tracking algorithms were rewritten to look not just for moving objects, but for ones that appear too still. But beyond the science, there was a quieter legacy, a shift in perspective. The universe had reminded humanity that stillness is part of motion, that silence is part of sound, and that understanding comes only when we stop long enough to see. Perhaps the comet hadn't truly stopped at all. Perhaps we had. Perhaps that was the point, because for one fragile moment between the stars and the sun, the cosmos held its breath and allowed us to hear it.